Jai Hind all, this is Assistant Professor Gagandeep Sin from Ajay Kumar Garg Engineering College. This is a lecture series on satellite communication complex topics, the topics which are not in the main subject, main syllabus, but are important to cover the main syllabus. Today's topic is the block diagram of satellite communication. This is important to understand the working of satellite communication as well as the all other aspects of the satellite communication that are discussed in the first unit as well as the later on all units. So if we see in a block diagram of a satellite, the general block diagram of a satellite can be given as the system, which is one is at Earth station, which I represent as Earth station. It has an at least one antenna. This Earth station may be a complex one, but for the simplicity we can take it as an antenna. For example, if we have a transmitter, that transmitter may generate some signal and it will transmit only with Earth station toward the satellite communication, toward the satellite. So there is a satellite that will that may be a passive satellite or an active satellite. The active satellite will receive this signal and it will process the signal and it will revert back this signal to the Earth's second Earth station or the same Earth station. So this is Earth station 1 or this is Earth station 2. Now another possibility is that the same signal is transmitted to the Earth station at the same point where it has been transmitted. So same signal can be used as the transmitter as well as for the receiver. So at that time this station will be not available. The same station will be acting as a transmitter and the same station will act as a receiver also. So the transmitter and the receiver both are at the same place. So if we see this general satellite communication scenario, we must have an Earth station, satellite as well as the Earth station, which is the receiver Earth station. So to draw the block diagram, so we must have one Earth station. That Earth station will have an antenna. This antenna will transmit toward the satellite, and from satellite a signal will be received that is transmitted to that will received by the Earth station 2. Earth station 2. To elaborate this signal, we have this communication. We have two signals that are being transmitted. Now the case when the transmitting and receiving antenna are nearby, for example for this satellite, the two antennas, transmitter and the receiver antenna, both are very near to each other and both are transmitting and receiving. So we must have something that differentiate between the passing input signal as well as the output signal. So to differentiate these two signals, one signal is uplink signal and other is downlink signal. Both signals have different frequencies and both are polarized. Uplink frequency is always taken as higher frequency and downlink is taken as a lower frequency, because for the higher frequency there will be more disturbance, there will be more attenuation in the atmosphere, whereas for the low frequency the attenuation will be lower. So we can accommodate more power at the Earth station to mitigate the effect of the atmospheric noise or the attenuation, whereas satellite size need not to be increased to overcome the losses. So when the signal frequency is low, we can have a lower satellite signals. So and so we must have a something that that mitigate the noise problem over here and noise plus power problem, here. So if we say we have a signal antenna, a satellite, a signal is being transmitted toward the receiver antenna. If this is a receiver, this receiving antenna must have low noise so that it can take the signal without adding up another further noise. So generally this antenna is taking the signals which can demultiplex as well as the uh, polarized multiplexing. So both this signal is polarized antenna. Generally horn antenna are used for the this antennas, this receiver. These antenna may be dish antenna or a concave antenna. So after this one, there we must have to use a low noise amplifier, LNA, low noise amplifier. This low noise amplifier generally do not have any power, noise power. So any power that is amplified is have the same signal to noise ratio as it is received. So the signal to noise ratio is not changing in this low noise amplifier. From this low noise amplifier, the signal is then processed as the receiver. As signal has processed in the receiver, transmitter, the same deprocessing is done and in this block. So after this one, there will be a signal that is the baseband signal. Similarly, when a signal is transmitted toward Earth station, as we have seen that for the uplink the noise is more, so we have to because of the frequency, so we have to make this signal stronger so that the signal to noise ratio do not have much higher values. So generally a high power amplifier is used which increases the power of the signal to increase the signal to noise ratio. So at the input we use signal high power amplifier which increases the uplink signal power. So by increasing the signal power, the signal to noise ratio is higher. The signal power is higher. So the noise power will be much more lesser than the here. So as much high as possible, the signal power is there. We try to take the signal power higher. So this high power will reduce the signal to noise ratio over here. The noise power will be much more lower as much as we increase the signal power over here. So before this one we process the signal here. So this processing signal is done for the baseband signal. Now this processing is, first one is encoding. This processing is encoding. The signal is encoded for the transmission. Then this encoded signal, is modulated. And then it also multiplexed. So correspondingly deprocessing used over here is decoding. Then demodulation, and then demultiplexing. So signal is decoded at the receiver after from low noise amplifier. Signal is decoded and then demodulated and then demultiplexed. So if we also include these in the blocks, the block diagram of satellite communication can be, first of all, we generate a baseband signal. This baseband signal can be a voice, or it can be a signal that is to be transmitted. It can be a mobile generated signal. It can be a communication system which is used for the DSB. So this baseband signal is then encoded This encoding is based on the type of the signal. The signal can be encoded in the form of line coding as well as in the form of different codes to reduce the bits, and all these things are done over here. After this encoding of the message signal, the signal is modulated. This modulation is performed according to the signals. Generally, the signals which is used for the satellite communication are for the low power as well as for the high power as well as the far distance away. So QPSK and phase shift keying is used generally for the satellite communication. After that one, there is multiplexing of the signals. This multiplexing a signal is done to accommodate the more number of signals. This multiplexing is generally time division multiplexing, FDMA, frequency division multiplexing, time division, or code division multiplexing. There are other form of multiplexing also. After that one, we use high power amplifier to amplify the power of the signal. This high power amplifier is then transmits the signal toward the satellite. As we have discussed also, that this signal that is transmitted from this antenna is polarized so that there can be another duplexing of the signals. This duplexing of the signal will increase the bandwidth utilization of the system. Further, the C by N ratio of the intersymbol interference of the different signals will reduced. So multiplexing is taking a number of signals, number of systems that are giving inputs. This polarized signal will increase that, further increase the number of the transmitted signals. So after this one, the satellite will reprocess this signal, and then this is transmitted toward the Earth station. This is transmitted toward the Earth station. So at the Earth station, we will have a low noise amplifier so that we do not have much higher received signal power, but received noise power, but the signal to noise overall ratio is maintained, that the signal is strengthening as well as the noise is not other noise is not added up. So from this one, after that one, we generally demultiplex the signals. Demultiplex the signals, and then from this demultiplex signals, we demodulate the signals. Demodulate the signals. This demodulation of the signals is corresponding to the different signals that is being modulated at the different phase. Then there is decoding of the signals. The decoding of signal is again the correspondingly encoded signal. If we use a trellis coding, then again we will use a trellis coding for decoding. If we are using some Hamming coding, then we will also use Hamming coding for the decoding signals. After this one, we are ready to receive the baseband signal. So this is the this is the transmitting earth station. This is the receiver earth station. So this is a basically a block diagram of the transmitter earth station and the receiver earth station. Now there is another system, that is a satellite system. This satellite system has different subsystems and is also have the different blocks for the telemetry tracking and control system, as well as for the communication. If we say for the communication system, this satellite will act as a band pipe transmitter or a reflector. Now for the simplicity, we can take this satellite as a passive satellite. Passive satellite. Now for the passive satellite, the signal will be received and then it is transmitted toward the earth station again. So this satellite will not have any active components. It will have some power supplies which is used for the telemetry tracking and control system, but for the signal processing it will not use that any power. However, if we are using if the satellite is used with some active component, with some active satellite is being used, then there is different transponders in that satellite, which we have discussed in the main topics of the unit 3, the subsystems and the communication system of the satellite. So in that one, we will have again some encoders, antennas, modulators, as well as the local frequency or local oscillators and the frequency multiplexers, frequency modulators. These frequency multipliers will multiply the signal to make it possible, make the signal possible for the changes. Then it down converts the signal by using this frequency multiplexers to transmit the signal toward the earth station. So all these blocks can be added for the satellite, but for the earth station, these are the basic block diagram of the earth stations. So with this earth stations block diagram, we can have a different system that may be possible to be eliminated. For example, for a point-to-point communication, we do not need a multiplexer. This multiplexer can be removed for a point-to-point communication or for a single user. For other type of signals, we can also use the satellite communication block diagram. So this is the satellite block diagram that is used for the complex topic. Thank you.